Okay, so lesson 8, now we're going to incorporate our translations as well as our stretches and reflections. So example 1, describe how the graph of the given function compares to the graph of y equals sine x, where x is in degrees. So here we have y equals the sine of x minus 30 degrees. We've replaced x with x minus 30 degrees. This means we've gone 30 degrees to the right. What about sine of x plus 2? Well, since that 2 is out of the brackets, we can use vertical translation, and we go 2 up. 3, we now have replaced x with x plus 60 degrees, so that means we go 60 degrees to the left. The subtract 1 means we go 1 down, so there's a horizontal and vertical translation. And 4, we can add 45 degrees to both sides. And now we see we went right 45 degrees, that's for the one inside the brackets, and we also went up 45. Sorry, that wasn't 45 degrees, that's just 45. We have special words for these when we're in trigonometry. A horizontal translation is called a horizontal phase shift, and a vertical translation is called a vertical displacement. So we use those words. It's not wrong to say translations. Just you'll see if it's written in a question, we'll usually refer to as phase shift or vertical displacement. So sine of x has no phase shift and no vertical displacement. When I think about phase shift, it helps me to think if I start at x equals 0, if my sine graph usually starts like this, has its minimum point there. If suddenly the minimum point has moved left or right, that tells me there's been a phase shift in my sine graph. My cosine graph usually starts at its maximum value. So if I have a cosine graph and my maximum value is not x equals 0, that tells me I have a phase shift. Here we have sine of x minus pi over 4, so that's in brackets. This means we've gone pi over 4. We're now in radians, but that does not change how it affects our graph. It's pi over 4 units, right? We have not moved up or down at all. Sine of x plus 5. So now we're not in brackets, so that means we don't have a phase shift, but we have gone up 5. Here we can think of it as plus pi on that side or minus pi on this side. So the horizontal phase shift, we have now gone 3 pi over 2 radians left, and we've gone up pi. So the horizontal phase shift is in radians. The vertical displacement is just in that angle there. Y equals the sine of x minus c plus d. What does this tell us? We've gone right c and up d. And what about if we incorporate stretch as well? As long as this b is factored out, we can say the same thing. Right C and up D. So don't forget what we learned in Unit 1. You always need to factor out that stretch. Again, would we expect the same thing for cosine? Yes, they're really the exact same graph, just with a phase shift. So it's actually, if you're testing the graph and you're not told whether it's sine or graph, there's no way of knowing. You can come up with an equation in terms of sine that gives you that graph, or an equation in cosine that gives you that graph. We tend to usually use sine for whatever reason. So changing the parameter c on the graphs of sine and cosine result in a horizontal phase shift with the following. So just like before, if c is greater than 0, that means this looks like x minus c. We move right. If c is less than 0, which means it ends up looking like x plus c, we move left. Changing the parameter d on the graph results in a vertical displacement, so we move the whole graph up if d is greater than 0, the whole graph down if d is less than 0. The vertical displacement is determined from a graph using the formula max plus min over 2. This is sometimes also referred to as the median line, the line that cuts the graph in half. So it's very similar to our amplitude formula. Amplitude is max minus min divided by 2. The vertical displacement, or the median, is max plus min divided by 2. Again, we're just going to focus on the sine and cosine graphs. We don't need to worry about that second part on tan. So the amplitude A is max minus min. The period is 360 divided by B. Again, those are always going to be positive, so we use absolute value of A and B. Horizontal phase shift, we move right or left, depending on the sign. The vertical displacement, up or down, or we can use this formula to help us from the graph as well. Example 3. Consider the equations on the formula y equals a sine b of x minus c plus d, and y equals a cos b of x minus d. Where a is 1 and b is 1, right? The equation we represent. A, a cosine function having a horizontal shift 75 degrees right. Well, 75 degrees right means we're going to go minus 75 degrees in brackets. B, a sine function having a horizontal phase shift of 3 pi over 5 radians left and a vertical displacement of 4 units up. So we move left 3 pi over 4, so we're going to have plus 3 pi over 4. Up 4, we can write plus 4 at the end. Find the amplitude, period, horizontal phase shift, and vertical displacement of the graph of the following. Well, amplitudes are always easy. It's just the vertical stretch. The period is where we have to do a little bit of math. It tells us here, since there's a pi here, we're going to say this is in radians. So we're going to go 2 pi over b, which is pi. Sorry, that's not our b value. 2 pi over 3 is our b value. It is factored out, which is speed. So that's going to be our period, 2 pi over 3. We'll leave it as an exact value. The horizontal phase shift, we've gone pi left. And the vertical displacement, we have gone down 4. D, amplitude is 2/3. The amplitude is not negative 2/3. We never consider an amplitude to be negative. The period, again, we want to make sure that that stretch factor is factored out, which it is. And now we can go 2 pi divided by 1/4. This actually gives us 8 pi is the period. Our horizontal phase shift, we've gone pi over 12 right. And the vertical displacement, we have gone 3 up. Example 5, find the amplitude, period, horizontal again. So now this is the case where they have not factored out the stretch. So we need to always start by doing this. These are standard of excellence questions. It's really quite simple. We just need to remember that. So we have to factor out 3. This allows us to see what the horizontal phase shift is. So we have an amplitude of 2. That's our A value. The period, we're going to go 2 pi divided by 3. Which is just 2 pi over 3 radians. A horizontal phase shift is now pi over 3 left. Right, so it's tempting from the original. It looks like it's gone pi left, but that's why we need to factor out that 3 first. The vertical displacement is down 4. Next one. Here our amplitude, well, there's just a negative sign in front of the cosine, which means it's -1 is the vertical stretch. So our amplitude is 1. The period, we're going to take 2 pi over b. Not forget to factor out that b value here. So we get x minus pi over 4 plus pi. So our b value is 2, well, 2 pi over 2 is pi. So our period's pi radians. Our horizontal phase shift, we've gone pi over 4 to the right. Right, it looked like pi over 2, that's why we had to factor it out first. And our vertical displacement, we've gone pi units. Next, the graphs from A to D represent the same trigonometric function. Write the equation of the graph in the form y equals a sine of x minus c, where if a is greater than 0 and there is a minimum possible horizontal phase shift. So you'll notice with these graphs, they can all be sine graphs, they can all be cosine graphs, they can all be reflections, they can all be phase shifts because these graphs repeat over and over and over again. So they give us some extra information to point us in the right direction for what equation they want. So here we're saying there's being no reflection. So A is going to be positive. It's also telling us to use a sine equation and the minimum possible phase shift. So we know that if we shift these right away, there's lots of phase shifts. Because if we look for what I refer to as the starting point, the original value of y when x is 0, there's an infinite number you can choose. We usually like to choose the smallest one. So the best way of doing this is just picking out all the information we can. So here we know that the amplitude is 4. You have a maximum of 4 and a minimum of 4. The period here is 2 pi, right? It starts here, goes here, it repeats itself as 2 pi, which means our b value is 1, which is what it referred us to here. Our horizontal phase shift. Well, sine originally at y equals 0 was at the y equals 0. So sine originally started here. We want the smallest possible shift. Well, the smallest possible shift would be here. So we need to find out what this value is. And that is going to be our phase shift. And this is pi over 3 in this case. This is pi over 3. Each tick is worth pi over 6. So we have a phase shift of pi over 3 right. So our original point was here. It's now over there. So that's pi over 3 to the right. And no vertical displacement. And also it didn't give us an option for one here. So we can go to our equation. A sine x minus pi over 3. Okay, well now, what if instead we wanted to... The amplitude stays the same, but now this tells us we need to use a negative a value. And this actually means we have to think of it different. Because if I'm thinking sine has a reflection, instead of going up from this point, it's going to go down from this point and go around. So this point was originally 0, 0 on the sine graph. So now I need to find the closest point on this graph, which means I go downwards. Well, the closest point on this graph is here, where I start at the middle and go down. So each is pi over 6. So this is negative pi over 6. This would be negative 2 pi over 6, or negative pi over 3. Negative 3 pi over 6. So this point would be negative 4 pi over 6, which is the same thing as negative 2 pi over 3. So now I've gone left 2 pi over 3. So I'm going to go plus 2 pi over 3. If this is really confusing for you ingredients, you can go ahead and graph this into green mode from negative 180 to 360. And your ticks are going at 30 degrees. It's a lot easier to kind of get our minds around where those are. But what if instead we want to write this as a cosine? So again, our a value is greater than 0. Our amplitude is 4. So we need to figure out what our phase shift is. Well, the cosine graph usually starts here at its maximum point and goes down. So I need to find the closest equivalent point on this graph. In that case, that's here. So pi over 2, that's 3 pi over 6. This would be 4 pi over 6. That would be 5 pi over 6 to the right. That I've moved. Now we're going to be looking at reflection. So now we do the same thing, but with a negative a value. The original cosine graph, if we we've vertically stretched it by 4, is now going to start at -4, 0, at its minimum point, and go up. So I need to find the closest point that does that, because we want a minimum phase shift. And in this case, that's going to be this point. This would be -pi/6. So I'm going to add pi/6. So all of those represent the same graph. This is a written question. It just says, give me a graph like this. I would have to accept any of those answers. All 4 of those would work. Or we try and direct you to one. So by saying things like this, telling you A must be positive, telling you whether we want sine or cosine. And usually we consider the minimum possible horizontal phase shift. But really, you could put it looking at this first one. If it didn't tell me to use a minimum phase shift, I could have also used that point and considered it shifted more than 2 pi over. This is infinite number of equations that way. Of course, if it's a multiple choice test, you just need to analyze the formulas. Consider the graph shown. If the graph represents a sine function where a is greater than 0, complete the table and write the equation represented by the graph. So now this is a little bit trickier because we do have a vertical displacement and we do have a change in period as well. So we're going to pick out this information. But again, you'll notice it does give me the information that a is going to be positive. And does it tell me whether I need to use sine or cosine? So we can just pick one. Graph. Oh no, it does say sine. The graph represents a sine function, so we're going to write it in a sine function. So the amplitude here, remember we can think of amplitude as max minus min divided by 2. So that's 1 minus -5 is 6 divided by 2 is 3. Period here, how long does this take to repeat? So we can pick from here, you just have to pick any 2 points. So you could use this point and this point. So this would be pi/3, 2 pi/3. This would be 4 pi/3, 13 pi/3, 14 pi/3. So the difference between those two is 12 pi/3, right? So subtract them. 14 pi/3 minus 2 pi/3 is 12 pi/3, which simplifies to be 4 pi. You could also have picked points like this and see it's some 4 pi. Doesn't matter which one. Then more the sine graph usually starts at its midpoint and goes up. You can also think of what the maximum is, but we know that this is the midpoint. If we look at the values, this is where we go up. So usually our sine graph starts at the midpoint and goes up. So this means we've got pi/3 units left. The vertical displacement cuts everything in half. So it would be -2. So now to put this into an equation, we just need to find out what our b value is using the period. So we know that our period for pi is 2 pi over b. So multiply by b, divide by 4 pi, we do have the value of 1/2. So this gives me y equals our amplitude times the sine of 1/2 x plus pi/3 minus 2. Write the equation if the graph in A represents a sine function where A is less than 0. So everything stays the same except our phase shift. We can change. So for something that's less than 0, well now instead of looking for a point from my midline that goes up, I need to find a point from my midline that goes down. So we know that each line here is pi/3. 2 pi would be 6 pi/3, so one less than that would be 5 pi/3. Whoops, I'm in the wrong spot. got 5 pi over 3 to the right. So we can also write this as minus 5 pi over 3. See, if the graph represents a cosine function, what are its possible equations? So everything is the same in this graph. The graph is identical, so the amplitude is still 3. The period is still 4 pi. The vertical displacement hasn't changed. What does change is our phase shift. So remember, cosine usually starts at its maximum point and goes down. So I need to find the equivalent point on the new graph, which is here. And this is at 2 pi over 3 to the right. So the equation would be, sorry, I'm now cosine, of our stretch is still 1/2, so that does not change. But it's now 1/2 x minus 2 pi over 3 minus 2. D says, what if a is less than 0? So again, everything stays the same except for that phase shift. And in general, with all of these graphs, the phase shift is the hardest one to figure out. So again, cosine has been reflected. Start at its minimum point and go up. So where is its closest minimum point to go up from the center would be here. Right, so if there was no displacement, I would start here at -5 and go up. So that must be this point. This is -3 pi over 3, so this must be -4 pi over 3. So I'm going to have plus 4 pi over 3. Last example, consider the graphs of y equals a sine b of x minus c plus d and y equals a cos of b of x minus c plus d. Changing which of the parameters a, b, and c affect the domain, first of all. The domain of all these graphs is all real numbers, so none of these affect the domain of the sine and cosine graph. The range, there are two things that affect the range, the amplitude and how far you've moved the graph up and down. So the parameters that affect the range are a and d. The amplitude, only a affects the amplitude. The period, only b affects the period. No matter how much you move something up or down, or left or right, you don't change the amplitude of the period. The zeros, well, what changes the x-intercept? And there are a few things here. The most obvious ones are b and c, but they are not the only ones. D affects the zeros as well. So that's why I think of it too, that of course it's possible is if we shift this graph up far enough, it's actually not going to have any x-intercepts. So definitely moving it up or down does change the x-intercepts. And actually, the amplitude can change as well, as long as d does not equal 0. So if I have this graph shifted all the way up there, but I have a bigger amplitude, instead, if I sketch this one, sketch this if it was the middle, I can actually make these graphs, whoops, what have I done? Right, these graphs can join like this, and they do still change how x-intercepts again. State the max and min values in terms of a, b, c, and d if a is greater than 0. Well, our max point, we can always find if we know our middle point, or our median line, our midline, and take d plus the amplitude. Our minimum point, we know the middle is at d, so if we minus the amplitude, we can also just say the absolute value of a, and that way we don't have to worry about if a is greater than 0. C, determine the range of the function y equals 3 sine 2 of x minus pi minus 4. So the range is based completely on what the max and the min is. So if the maximum value of this graph, well, we know our midline's at -4, our amplitude is at 3, so that means our maximum point must be -1. Remember, the maximum is always the y value. The minimum point, we start at that midline of -4. We subtract our amplitude, we get -7. So, oops, I should write smallest to biggest. our range in interval notation would be like that, or you could say y is between negative 7 and negative